Chapter 8 is all about bonding. When we're going through Chapter 8, there's a few questions that you should be asking yourself. First, what is meant by the term chemical bond? Why do atoms bond with each other to form compounds? And also, how do atoms bond with each other to form compounds? Section 1 is a generic introduction to the types of chemical bonds. There is no real good way to define what a chemical bond is. It's difficult to give a simple definition that is also a complete definition. We're going to go with forces that hold groups of atoms together and makes them function as a unit. In general, a bond will form if the energy of the two units bonded together is less than that of when they are separated. This picture here is looking at an interaction of two hydrogen atoms. So on the top, you have two hydrogen atoms, the positively charged nucleus and the negative electron, and the little dots just sort of indicate the places where that electron might be. And at this point, they are far apart enough so that there is no interaction. But as they begin to get closer, they actually begin to interact with each other. When they get to an optimum distance, and we'll talk about the optimum distance in a second, then that distance is dictated by the lowest overall energy of the system. So why do atoms bond with each other to form molecules? They're going to bond if the energy of the aggregate is lower than that of the separate atoms. So here we're looking at a description of the potential energy over the distance between the molecules. And what you can see is that there is a point in which the distance between the two molecules is optimum when you consider the amount of energy that's present. So they are forming molecules to be more stable. A couple of key ideas in bonding. In ionic bonding, electrons are transferred. In covalent bonding, they're shared. Now there is some descriptions of intermediate cases, and I'm going to give you a few numbers to use. But first, let's talk about those intermediate cases. You can have a polar covalent bond, and that is when there is unequal sharing of electrons between atoms in a molecule, and that's due to a charge separation in the bond, where you're going to have a partially positive and a partially negative charge. So how would you know you have that? One way is to use an electric field, and if we had a series of hydrogen fluoride molecules that are bound together, in the presence of no electric field, as you see in A, there is no real orientation to the molecules. But once an electric field is applied, then the molecules will line up in a particular fashion. That is indicating that there is a polar covalent bond. We're going to continue on into electronegativity. We've talked a bit about electronegativity already, but we're going to get a little bit farther into it. The definition of electronegativity is the ability to attract electrons to itself. For a molecule that would be HX, X kind of being an unknown element, the electronegativities of H and X are determined by comparing the bond energy that you have with that HX bond to what would be the expected bond energy. Now, what I'm going to have you guys use are these numbers here when determining if something is ionic or covalent. It's a little bit difficult, but in general, we're going to use the electronegativity values and we're going to compare it. If the difference in electronegativity is greater than 1.7, then we would consider that an ionic bond. If the difference between electronegativities is somewhere between 0.5 and 1.7, then we will call that a polar covalent bond. When that is, they are sharing electrons, but the distribution of the electrons are somewhat unequal. If the difference in electronegativity is less than 0.5, we will consider it a pure covalent bond, meaning that they are sharing electrons. Here is a table of electronegativity values. In class, I will give you another. They are pretty readily found and definitely in your textbook. On a periodic table, electronegativity values generally increase across a period and decrease across a group. The range of electronegativity values is 4 for fluorine, which is the most electronegative, and also zero point 0.7 for cesium, which is the least electronegative. Now remember, when I say that the electronegativity increases across a period and decreases down a group, I'm talking about a trend, and I'm not talking about, if someone were to ask you why, that's not a good enough answer yet. So let's quickly just see how we're doing. If lithium and fluorine were to react, which has more attraction for an electron and why? So think about that for a second. Pause it if you need to. For the first one, fluorine will have more attraction for an electron than lithium. They both have valence electrons in the same second principal energy level, but fluorine has a greater number of protons in the nucleus. Electrons are attracted to the larger nucleus. For the second one, in a bond between fluorine and iodine, which one has more attraction for an electron and why? Think about it. Pause it if you need to. The correct answer again is fluorine. It has more attraction for an electron than iodine. In this case, the nuclear charge of iodine is greater, but the valence electrons are at a higher energy level, and then which gives us some shielding that occurs between them. Now, here's the question that I alluded to a couple of slides ago. What is the general trend for electronegativity across rows and down columns? And explain the trend. Pause it if you need to, maybe jot it down. Okay, generally speaking, the electronegativity increases going from left to right across a period, and this is because the number of protons increases, which increases the effective nuclear charge. The electronegativity decreases going down a group because the size of atoms increases as you go down, and so when other electrons approach the larger atoms, the effective nuclear charge is not as great, and that's largely due to shielding from the current electrons that are already there. Another thing to look at is the relationship between electronegativities and bond type. So if there is no electronegativity between atoms, then it's going to be a covalent bond. And remember, I told you if the electronegativity difference was less than 0.5, we will consider it a covalent bond, and it'll have high covalent character and low ionic character. If the electronegativity is intermediate, and we said between 0.5 and 1.7, we would consider that a polar covalent bond. And what's interesting about polar covalent bonds is they have somewhat of a covalent characters and somewhat ionic characters as well. If the electronegativity difference is large, I said greater than 1.7, we'd consider an ionic bond. And in that situation, they would have high ionic character and low covalent character. The next part is to arrange the following bonds from most polar to least polar. If you haven't already, grab a textbook or look up a sheet of electronegativity values so that you could follow along with these problems. Go ahead and pause it, work on it, and then we'll come back. All right, for letter A, we're looking for the greater electronegativity difference between the atoms. So that will be the most polar bond. So for A, the most polar bond occurs between carbon and fluorine, then nitrogen and fluorine, then oxygen and fluorine. For B, we have these, and for C, okay. Next up, which of the following bonds would be least polar yet still be considered polar covalent? Think about it, pause it. The correct answer is a bond between nitrogen and oxygen. It's to be considered polar covalent, there must be an unequal sharing of electrons. So in this case, you would want to choose the bond with the least difference in electronegativity, yet you don't want the values to be equal like you would have between oxygens. Next up, which of the following bonds would be the most polar without being considered ionic? if you can't remember the numbers that we went over before, you can also consider that to be considered ionic, generally the bond must occur between two nonmetals. So the most polar bond between nonmetals occurs with the bond that has the greatest difference in electronegativity, which is here. All right, so that was a basic introduction to types of bonds and electronegativity.